All right, hello calculus. This is lesson 6.3, but once again, we're going to start with these must-knows. Again, hopefully you know all of these, and you're just reading them off. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tangent is secant squared. The derivative of cotangent is, got a C, so it's negative cosecant squared. The derivative of secant is secant tangent. Secant x, tangent x. The derivative of cosecant, it's got a C, so it's negative. That's going to be cosecant, don't forget your x, oh Lord. Cosecant x, cotangent x with a negative. The derivative of e to the x is e to the x. A to the x is also exponential, so it's a to the x times the natural log of a. The derivative of the natural log of x is 1 over x. See it? 1 and the x, 1 over, okay. This is also a log function, but it has a different base. So this is 1 over x, and then divided by the natural log of a. All right, there you go. Hopefully you know all of those cold because that's really important. We also did the integrals. So good to know those as well. All right, so this is the reverse chain rule. Going to learn some pretty complicated stuff, but I think you'll like it. It's pretty easy. Turns out to be pretty easy. So we're going to be able to identify the chain rule in the integrands that we're looking at. And when we can't identify the chain rule or complete the chain rule, then we'll be using U-Substitution to do some more complicated integrals. So you have a worksheet today, and you do not need to submit. I have worked out the full solutions. The full solutions are available to you. Please, you need to do this. Like, this is every integral problem is a reverse chain rule on the AP test. So you need to know how to do this. This is huge on the AP test. So do not skip this assignment. You need to do it, but the whole solutions are worked out for you. So just make sure you get Wednesday's assignment submitted, and then this one you can work on a little bit every day because it's going to take some time. It took me 2 hours, I think. It was 11 o'clock at night, but I was doing it. I did it all. Okay. So this was the derivative of a composition. And this is way back. I want to say in Unit 2, way back. So we had this inside function and an outside function. And if we wanted to find the derivative, this was where the chain rule came from. So it would have been f prime, so the derivative of the outside, times g prime, the derivative of the inside. And so that's what we want to look for when we have an integral. So if we wanted to integrate something, we'd want to see right here, which is the derivative of the inside. Some inside piece, whatever that inside piece is. And if you see it, then that piece just sort of disappears and you're just left with that outer function. So it's kind of nice. Let's see how it works a little bit more in depth. So just for giggles, let's do these chain rule problems. So we want to find the derivative of 1 plus 5x all to the 4th power. So again, we have this inside function, but to get to it, we have to do the outer piece first. So our power comes down. We don't touch the stuff on the inside. This reduces by 1, and then we multiply it by the derivative of the inside. Well, the derivative of 1 is 0, and the derivative of 5x is 5. So there again is that what I'm going to call U prime, right? So that's that inner piece. So if this whole thing is the inside, I'm going to call it U, then this is just the derivative of U. Okay. Great, we're gonna leave that there. Here, of course, you can multiply the 4 and the 5 together, but that's not the point of this exercise. So once again, we have the sine function, and it's got this other function on the inside. I'm going to call that the u function. And so if we want to find the derivative, we're going to take the derivative of sine, which we know is cosine of the function, and then we're going to multiply it by u prime. So the derivative of 1 is 0, and the derivative of 5x is 5. All right, so there's our u prime. So now we have this function that we want to integrate. And when I'm looking at this, I'm seeing, hey, look, here's this inside function. There's that u function that's to the third power. And when I look here, there's this thing being multiplied. Well, hey, that happens to be u prime, the derivative of that inside piece. We've already got it multiplied on. Well, when we do a derivative, that chain rule u prime appears. When we integrate, the chain rule disappears. So this u prime disappears. All right, this says the chain rule appears. Chain rule appears. And so if we're integrating, then that u prime, that chain rule piece will end up disappearing, which is kind of nice. So if you see it, it makes life a whole lot easier. And now all I have to think about then is just taking this function, increasing the power by 1, and dividing by the new power. So here we have 1 plus 5x. We're going to increase to power 4 and divide by the 4. Don't forget your plus c. And that's it. That chain rule thing is going to disappear. Well, how do you know if you did it right? Well, we can take a derivative. So if I take a derivative of this, let's test it. Let me get a different color pen here. Pink is good. All right, so if I were to take the derivative of this, just to check, so 1 plus 5x to the 4th divided by 4, I would drop my power, reduce the power by 1. It's over 4, but I have to remember I have to multiply by the chain rule here, the derivative of the inside, 0 plus 5, so just 5. And you'll see the 4's cancel out, and we're left with 5 times 1 plus 5x all to the third power. So, oh, you can't see that. Oh, my bad. There you go. All right. So you can see, when in doubt, check it out. It just works in so many situations. Okay. So once again, here I have this inside function. I'm going to call that the u function. We like to see just a plain old x there, but it's not a plain old thing. It's a big old complicated u mess. And when I look here and I think about, hey, what's the derivative of this thing? Well, again, it's right here. Here's that u prime thing. So I'm taking into account that chain rule piece is here. So when I integrate, it's going to disappear. That chain rule piece disappears. So all I have to worry about is this stuff. The integral of cosine is sine, right? Is that right? The derivative of sine is cosine. Yes. So sine of 1 plus 5x, that's it. Plus c. There you go. Kind of cool. And again, you can always check by taking a derivative. Oh, we did it already. It was right here. Again, the derivative of sine is cosine of the function times the 5. So there it is, back where we started. I did this so many times on the AP test where I was like, I don't know how to integrate that, but I can take the derivative of every single answer there. Those are really great, cheater's method on the AP test. Totally not cheating, totally valid. They ask you to integrate, you can always take a derivative of the answers. Okay, so what we want to think about doing is trying to complete the chain rule if it's not present, all right? So here I have this U function, and if I were to see the chain rule present, then this would be really easy to do. So how do we do that? How do we create something, manipulate something that makes it really easy for us to integrate? Well, what I would like to see is I need to see that U prime. Well, okay, let's see. What can we do here? So I have 3x minus 1 to the 10th power dx. And so what I need is a U prime. Well, what is U prime? U prime, the derivative of this inside piece, the derivative of 3x is just 3. So if that 3 were there, then I'd be totally golden. I got my U, I got my U prime, and that's great. Okay, but I can't just multiply by 3, can I? I can cancel it out though. If I not only multiply by 3, but I also multiply by 1/3. And you're like, but wouldn't you just pull out the 3 and then cancel it out? Well, yes, I would. But we don't want to do that because we need to be able to see the function and then its derivative as well in order to integrate it. And so, in effect, what we're doing here is multiplying by 1. So it doesn't change what we've started with, but it makes it easier to manipulate. So we get this 1/3. And then all we have to worry about is our U, 3x minus 1, increase the power by 1, and divide by the new power. So divided by 11 plus C. That's 1/3 times. So that becomes 3x minus 1 to the 11th over 33 plus C. And that's it. It's kind of cool. All right, so that's completing the chain rule. So let's look at this one. Sine of 4x dx. So here is our crazy U function. And what we need is U prime. Where is U prime? So what I'm going to do is just put it on. The derivative of this 4x is 4. So we're going to multiply by 4. But to keep things balanced, I'm going to put a 1/4 on the outside as well. Could I drag the 4 outside? I could. But then I don't know how to integrate this. So I need the U prime there. And then all we have to do is integrate the outside function. So the outside function, the derivative of cosine is negative sine. So I need a negative cosine of 4x plus c. So this becomes negative 1/4 cosine of 4x plus c. Good. The derivative of cosine would give me a negative sign, so I need that extra negative so it goes away. All right, there we go. All right, here, this is the cosine of t squared. And you can see I would normally have to, if I were differentiating, have to take the derivative of t squared. The derivative, let's see, if this is my u portion here, this part, derivative would be 2t. I have a 3t. I can't just subtract the t. That doesn't work. What I can do is I can pull this 3 out in front so that I have t times cosine of t squared dt. So here is my u portion. And the derivative, u prime, would be 2t. So now my u prime portion is present, but I can't just randomly multiply by 2. I must also divide by 2. So I'm going to put a divide by 2 out in front. All right, so this becomes 3/2. Now that derivative, the baby is just going to disappear. Disappearing baby. God, I wish. Now we can just worry about integrating this outer function. So the integral of cosine is sine, because the derivative of sine is cosine of t squared, and then plus c. And again, you can always check to make sure that you're doing it right. I don't know where that problem came from. I'm most curious. I hope that's right. All right. Here, this is interesting. This sine squared of t, remember, really is sine of t quantity squared. And so we have this outer function, this whole thing is the u that's being squared. Well, what's the derivative of u? What's the derivative of sine of t? The derivative of sine t is cosine t, so u prime is present and accounted for. All right, cool. So the baby disappears, and all I'm left with is integrating this outer function. So the 2 increases to a 3. And we divide by the new power. Kind of cool. Again, disappearing baby. So what I want to point out is you have the calculus cheat sheet, the trig and calculus rules. This is posted in Clever. And if you haven't printed it yet, super easy. But you can see all of the integral rules down here, and they're in U form. They're not really in U form. Oh, that's so funny. I thought they were. Oh, well, maybe I'll have to give those to you then. That is so funny. Well, never mind. Forget what I was going to say. But if you haven't printed this off, you really, really should. It does have your unit circle here as well, and a whole bunch of formulas like your Pythagorean identities, which are super useful, and of course, lovely geometry formulas. So all good things that you want to make sure that you have at your fingertips. All right. Cool. Got a couple more. All right, well, letter E is a little bit different here. I see an inside function. So if this was my U function, my complicated inner function, I would want to see the derivative. Here's the problem. U prime would be 3y squared. Now, I could certainly multiply the inside by 3y squared, but I can't move it to the outside to, balance things out. I can't divide on the outside by 3y squared because this is a variable. We can't pull it outside the integral because then we're not integrating the variables, okay? The only time the chain rule works is when we're simply multiplying by a number, which is what we've done on each of these. Okay, so this was multiplying by a variable, and I can't multiply it on the inside and multiply it or divide it on the outside because then I wouldn't be integrating the variable, which is a problem. So this one is actually not a chain rule at all. We don't even have to think about it. Actually, the easy thing to do is just turn this into a polynomial. Expand it. This is easy to do. All right, we know if it was just powers without any grouping symbols, then this would be super easy to do. So write it out and multiply. Let's expand this sucker. So this would be y cubed plus 1 times y cubed plus 1, which of course would be y to the 6th plus 2y cubed plus 1. dy. And now it's a wonderful polynomial, and we just have our power rules that we can apply here. So increase the power to y to the 7th and divide by the 7. So increase the power to y to the 4th and divide by the 4. And then here we would just have y, don't forget your plus c, and cleaning it up, 1/7 y to the 7th plus 1/2 y to the 4th plus y plus c. All right, same thing here. Technically, I could multiply these together. There's the dt on there. So we could totally multiply these things together and again, sort of just expand it into a giant polynomial. And that would be super easy to do. I was just making sure I did proper variables on the last one. Okay. So we can't, that one doesn't work. We can't do that method. So we could expand this if we wanted to, but if I look carefully, here is this fairly complicated function. If that's my u, and when I look carefully at this, it's u prime. 3t squared is the derivative of t cubed, and 2t is the derivative of t squared. So I have the mother function and its baby. So if I want to find the integral of this, all I have to do is integrate the mother. So increase the power and divide by the 4 there. Increase the power, t cubed. Don't forget your constant of integration. Oh, wait a minute. That is not right. Oh, pause. Let me think. Hold on a second. Let me look. Yeah, totally wrong. So we have to think about this as something to the first power. So really simple. This would be whatever's on the inside, increase the power and divide by the new power. So whatever's inside stays the same. Don't forget the plus c. So this is perfect. And of course, if you wanted to multiply all this together and then integrate, you'll get the same thing here, which is kind of interesting. So when in doubt, check it out. You know, you can always multiply these together. It's super easy. All right, here, this requires a whole lot of rewriting. And so I'm going to go ahead and do that. I have 6x squared, and then this is 4x cubed minus 5 to the negative 1/2 power dx. Okay, so I definitely have this inner piece here, this u function. So u to the 1/2 or u to the negative 1/2, that's easy to integrate. When I think about the baby here, u prime would be 12x squared. Bring down the 3, multiply those together, and then reduce the power. I have 6x squared, so I'm close. All I need to do then is multiply by 2, and there appears my u prime, my baby. But of course, if I multiply by 2, I also need to divide by 2 just to keep everything balanced. So now, baby disappears, and I can integrate u to the negative 1/2. So I'm going to increase my power. So I'm adding 2 over 2. So that would be the u, whatever that function is, to the 1/2 power. And we're going to divide by 1/2, which actually is just a times by 2. Don't forget your plus c. So it's really just 4x cubed minus 5 to the 1/2 power plus c, which is super handy. All right. Very cool. All right, so that's a great method, completing the chain rule there. But we also have U-substitution, which can get a little complicated, and I'm going to go fast so we only have one video here. I can't do completing the chain rule here. The derivative of x is just 1, so we have an extra x here, which is a problem. I don't know what to do with it. I can't pull it out. So we can't do the complete the baby here. So instead, we're going to let u equal whatever that inside function is. So this inside piece, whatever looks like it's inside, you guys can see that. And then we're going to go ahead and differentiate. We're going to take an implied derivative here, the derivative of u with respect to x, du dx, and well, I guess that's a d dx of both sides, if I was doing proper notation here. The derivative of x with respect to x, dx dx, is just 1. And then I am going to go ahead and move that dx to the other side. So we get du is equal to dx, 1 dx. You should also know that if u equals x minus 1, I can solve for x. So x would equal u plus 1. And that's going to be really useful for us. So let's see what we've got here. I can now change this integral to be in terms of u. So now here's this x. There's x. I'm going to replace x with u plus 1. And then originally we said this was u, so this becomes u to the 1/2 power. And it turns out that dx is equal to du. So dx becomes du. So everything is sort of traded in. Now we can actually use some exponent properties and distribute here. Clean this up. So this is u to the 1st power, which is the same as 2/2, and we can add these exponents together. So that gives me u to the 3/2, and 1 times u to the 1/2 is u to the 1/2 du. And now that's just the power rule. So I'm going to go ahead and increase my powers. So that becomes u to the 5/2 divided by 5/2, or multiplied by 2/5. And again, we're going to add 2/2. That becomes u to the 3/2 divided by 3/2, or multiplied by 2/3. Don't forget plus c. And then, of course, we did not have u's in our problem, so we need to transfer back into x's. So we get x minus 1 in place of the u. And then 2/3 x minus 1 to the 3/2 plus c. All right, let's try one more. And hopefully I can squeeze it in 4 minutes or less. All right, so first things first, I'm going to do a little bit of rewriting here. Actually, I'm not. Here is my inside function. So again, the derivative is just 2. I have way too much stuff here that I can't deal with. So I have to do U-substitution. So we're going to let u equal 2x plus 3. And while I'm at it, I'm going to go ahead and solve for x. So x would be u minus 3 divided by 2. Subtract the 3, divide by the 2. Good to know. Then I can go ahead and take a derivative. Du dx. Here, the derivative of 2x is just 2. And again, I'm going to do a little swap-a-toolie here. Multiply the dx to the other side and move the 2 over, divide by 2. So we get 1/2 du is equal to dx. So let's do some trading. So I have the integral of. Now, again, I'm going to replace this x. I need everything in terms of the same letter. So we have 2, and in place of x, u minus 3 over 2, minus 1. That's the numerator. And then I have 2x plus 3, which we said was u. So that's going to be u to the negative 9 power. And then dx is equal to 1/2 du. So everything is being multiplied together. This 1/2, I'm going to pull out in front. The times by 2 and divide by 2 end up canceling, which is kind of nice. And so I'm left with u minus 3 minus 1, which would be u minus 4, times u to the negative 9th du. Now I can go ahead and clean up my exponents here. So I get 1/2 times the integral of, this is u to the 1st. Same base, we're going to add those exponents together. We get negative 8 minus 4 u to the negative 9th du. And now we can just use our power rule here. Now that 1/2 is multiplying this whole entire thing. We're going to increase our power by 1. So that's u to the negative 7th, and then divide by the negative 7. And we have 4, this again, u, increase the power by 1 becomes negative 8, and divide by negative 8. And then there would be a plus c in there. And again, that 1/2 is multiplying everything. That's super important. So that gives us negative 1/14 u to the negative 7th. I'm going to plug in my 2x plus 3. And that becomes positive 4 over 16, which would be 1/4. In place of u, 2x plus 3 to the negative 8th. 1/2 times c is still just a c. Doesn't matter that it's changed. So that doesn't matter. That's it, ladies and gentlemen. That is U-substitution in a nutshell. Let me know if you have any questions. I am waiting to help you. All right, folks. Have a good day.